Hi, everyone.
Sure.
Welcome to the guest lecture of DeepRob. So it's my great pleasure to have Dr. Sai Vemprala, who is a senior researcher in the Autonomous Systems and Robotics Research Group at Microsoft, Seattle. He received his PhD from Texas A&M, and his thesis was focused on collaborative localization and uncertainty-aware navigation for groups of micro air vehicles. He's an expert in computer vision, machine learning, especially robotics, when it comes to ground vehicles and air vehicles. At Microsoft, Sai has been working on very exciting topics such as foundational models, especially for vision and robotics, perception planning, representation learning, learning from demonstration, data-driven simulations, and many, many more. He's a close friend of mine. And every time we meet, we have exciting conversations, and I always learn from him. So I'm super excited to have him here and talk about some recent research he's been doing at Microsoft. So Sai, welcome and take it away.
Hey, thanks so much for the great intro, Karthik. And hey, everyone, it's my great pleasure to be here giving this talk. And I think Karthik covered a lot about me already, so I don't have to do much. So yeah, I would love to talk to you today about some of the recent research at the Autonomous Systems and Robotics Research Group that I was involved in. And mostly I would like to center my talk around the concept of foundation models for autonomous systems and robotics. So we all know the kind of immense success we've seen with pre-training and large machine learning models in the domains of language and computer vision, right? So all of us are probably very familiar with GPT now, with given ChatGPT and GPT-4 open pretty much. Similarly, for the last few years, we've seen a lot of success with image-to-train data sets or image-to-train models and language models that have crawled the internet and things like that, and how widely applicable they can be to a broad range of tasks. And recently, we've kind of started calling them foundation models after the name was coined. And the initial foundation models paper kind of defines what foundation models are. Basically, neural networks that are trained on large masses of data, generally with self-supervised learning or unsupervised learning. But the key is that these are the models that can essentially form the backbone for pipelines that can accomplish a broad range of tasks. And so far, we have seen a lot of interesting tasks that large language models can do, and specifically in computer vision, how vision models can be adapted to autonomous systems and robotics and so on and so forth. So what does it take to really solve the robotics problems? So when we think about robotics, we are all too familiar with all of the challenges that come with it. We have several form factors, right? Because we can see warehouse robots, assembly robots, robots that do maintenance, delivery, aerial, ground, all of these sorts of things. And they all come with very unique challenges of their own, which can be due to their dynamical constraints, due to the out of distribution data that essentially they're faced with. All of this long tail of scenarios that is really hard to capture, even with demonstrations. So far, robotics has been a field that has kind of relied as much as possible on classical, handcrafted, and sort of task-specific modules to some extent. And this leads to a lot of scalability issues. And even though there is an advent of AI, in a lot of these places, especially in the perception space, it still takes a long time and effort to really construct a pipeline that can solve even a niche autonomy task for one specific form factor or one specific scenario. And you can see there are, tons of companies out there that try to essentially solve one particular problem, and it takes them a long time, because you have to curate the right kinds of data, you have to curate the right kinds of models and the training pipelines. And the deployment and monitoring and refinement process is extremely long, right? So these are several of the scalability issues that we'll have to solve if we were to even think of the notion of a general machine intelligence sort of a thing. So now, how do we marry these two concepts? Like, how can we leverage the success or learn from the success of foundation models in other spaces? And how do we bring that into robotics? Right? So I think that's sort of the main question that drives a lot of robotics research today. So what do we need for that, right? Obviously, the very first thing is the data. When it comes to any machine learning pipeline, foundation models, or whatnot, the biggest challenge with robotics, obviously, is the data, because it's really hard to gather data from all of these different tasks and robot form factors and everything. So far, a lot of the research is focused on how much can we leverage expert demonstrations. how much can we leverage, simulations or synthetic data? And this is, again, a big focus of a lot of the foundation model work as well. And at the same time, robotics is an applied field. And there is nothing that prevents us from using pre-trained models, right? So as opposed to having to construct and solve something end to end, there is a question of how much can we leverage existing models and the body of knowledge that is being encoded in some of these computer vision language models. But post that, imagine we do have some of this data that's sort of like catering to the specific tasks or domains. What do we need to understand? Right, so let me maybe just quickly use this. So what does a robotics foundation model or a pipeline of foundation models here needs to understand? Some of the core things are obviously basic notions about geometry and semantics, and this has tight connections with object recognition, things like safety, because you'll have to kind of like map out the environments and figure out what are safe areas and what are unsafe areas and things like that. Similarly, understanding of its own dynamics and the world model, like what happens in the future if I take a certain kind of action. This is obviously the perception action loop, or the state, the observation to state and then to action kind of a mapping. So it needs to encompass like this, a massive area of subtasks in order to actually achieve something autonomously. And this is usually done in terms of, we can think of this as several modules. We can have object-centric modules such as recognition, pose estimation. It could be grasp detections, affordance detection, stuff like that. For mobile robotics, obviously, the focus is more on localization and the mapping of large environments and spaces. And then we'll have to think about path planning, trajectory planning, reasoning over like behavioral stuff. Safety is of paramount importance. And last but not the least, it needs to be somewhat interfaceable, right, for human interaction. And that's where a lot of the language component comes in. So that's a lot of stuff, right? So for a foundation model, or at least a collection of models to be able to achieve autonomy, we will have to have some either implicit or explicit notion of a lot of these things. And it is an uphill battle for robotics to get there, right? So what I would like to talk to you today about is some initial works in this space from our group, which is mainly focusing on, I would like to, kind of bucket them into two categories. The first category is the representation learning aspect. And I'm talking about two papers here. So one of them is called PACT, which stands for Perception Action Causal Transformer. And I'll talk to you about how we've tried to learn from the sequence modeling kind of problem spaces and try to bring that into robotics in the form of pre-training. And the other one is called, it's a control barrier transformer for safe policy learning. And this is an extension over PACT, and it's a representation learning algorithm, again, that has an explicit focus on safety. And after that, I also want to talk to you about a couple of works in the language and robotics space. And this is a very recent foray of ours. These are, again, a couple of papers which you might have, some of you might have heard already, which is, one of them is a language trajectory transformer. It's, again, a transformer-based model that can essentially do human interactions through language inputs and modifying trajectories accordingly. And then finally, some of our most recent work was on trying to see how much can ChatGPT specifically help with robotics, given its large scale of understanding of several things, including code and geometrical concepts, just common sense reasoning, all of that stuff. So yeah, so that's kind of how I want to structure this. And a focus that I want to also mention in a lot of these works is increasingly we are trying to see how general these approaches can be, like starting from PACT and all of these things and all the way to ChatGPT for robotics. Because at the end of the day, that's what we want our foundation models, our machine intelligence to do. There is no, restructuring of intelligence for a new task. It's about adaptation. A lot of the common sense, a lot of the constructs that will be reused should still be preserved in the models that we use as the backbones. And how quickly can we adapt them to new tasks or new robots and everything? That's sort of what we want to get to. Okay, so initially, let's start with the representation learning for robotics concept, right? As you might have seen with GPT or BERT or any of these large language models, the whole idea is that when we throw large corpuses of text at them, they sort of learn the notions of grammar and semantics and essentially try to preserve them over large parts of text and things like that. And as a natural side effect, this leads to those models kind of automatically solving things like sentiment analysis, or just coming up with new textual pieces and things like that, and also kind of understanding and summarizing other pieces of text and things like that. What is the robotics equivalent of a GPT? That was the question that drove us when we first started looking into this area. And really, if we were to collect, essentially similar to the corpuses of text for GPT, if we were to collect large sets of trajectories, which are state action pairs or observation action pairs generally, how much can a model build sort of like a mental understanding of what this interaction means? And if I am sitting at a certain position, if I'm looking at the environment in a certain way, what is the most optimal action for me to take? And as we chain these sort of like sequences together, can the robots or the agents sort of learn how to navigate or learn how to behave and things like that? This is an idea that was actually explored by this paper called Decision Transformers, this seminal sort of like sequence modeling for RL paper. And it included the notion of observations and actions as well as rewards. So you could sort of like tune these models to give you optimal trajectories to solve a certain RL task. And we took a slightly different spin on that. And then we said, let's try to use, like these transformer-based decoder modules, just like GPT, but let's try to train them in a task-agnostic fashion. And that's what we are calling PACT, the Perception Action Causal Transformer, which is an autoregressive transformer that is training on state action or observation action pairs. And let me go into a little bit more detail on how it really works. So again, the raw data, which I'm kind of showing at the bottom here, it's basically something from a trajectory. A robot is navigating through, let's say, a hallway or something like that, and you are recording all the images and maybe the steering angles that go with each time step. So you have these like ST-1, AT-1, ST, AT, and so on. You have a sequence of states and actions. The very first thing we do is we tokenize them into a high dimensional feature space. So corresponding to each of these raw images or whatever sensor data we might have, we'll get a bunch of tokens. And after that, essentially it's just a transformer with a causal mask. So at every time step, it is only looking at what's been happening in the past. So for example, for this particular time step at time step T, it only has access to all of the the tokens in the past, as opposed to a BERT-like model, which does bidirectional access. So really, at the end of the day, what is this model trying to do? It's trying to learn from the sequence and what has happened all throughout the past. And it's trying to basically achieve two objectives. The first objective is through what's called a policy. We're calling it a policy head or a policy model. The embeddings of the transformer, after going through several layers, will now be used to predict what would be the most appropriate action for me to take. If I see a state at T-1, what should I do? Right, so that's the first thing. So it's really learning whatever is the behavior that's been encoded in the training data set. So essentially like learning from demonstrations, right? And the other thing it's trying to do is it's also trying to encode implicitly a world model of sorts. So for any time step, given, let's say, ST-1 and AT-1, this idea of a mental model means the robot should understand, what would be my next state if I were to take this particular action. And over a large, set of trajectories, a massive data set, this would hopefully include a lot of different kinds of behaviors, a lot of transitions. So it has a more holistic understanding of, given a state and a particular action, what would happen next. And you would try to use this eventually to, come up with different kinds of behaviors or trajectories. But at the end of the day, yeah, this is the entirety of the PACT architecture. And really, these are the pre-training objectives that we used. So training on this large unstructured kinds of trajectories, can we try to have this transformer try to predict the appropriate actions as well as whatever states will be coming next? So this was trained almost entirely in simulation. So we used the Musher car, which is basically like a small robot car platform out of University of Washington. There was a, I'm sorry. Sorry, I'm trying to I don't know if I can mute it, but it's basically except from our video, but So basically, we tried this out on 2 platforms. So one of them is the Musher car, which has a LiDAR sensor. So it gives you a 2D sort of scan of the surroundings. And similarly, also with habitat simulation, which is slightly more realistic with household environments, and it gives you an RGB image. And the Musher uses continuous action. So it's actually a steering angle as the action. And the habitat is about discrete actions. So it's the main difference. And yeah, so essentially what the very first thing PAC tries to learn is the resultant policy, which is trying to mimic what it has seen in the entire data set. So for example, if the car has been driving around in hallways in a safe manner, it essentially tries to learn how do I drive safely. But the more interesting thing is something like this. You can already sort of see that this is a sequence modeling problem, and it can be prompted, just like we would prompt a large language model. So we can prompt back in different ways. And for example, if I prompt it by saying, let's take a trajectory with mostly straight actions, like just driving straight, no turns, that's what the eventual distribution that it comes up will look like. And if I prompt it with, for example, wherever I see an intersection, I kind of turn right. And that's what the final rollout of the policy would look like. So this heat map is essentially showing like how PAC is trying to mimic what's been shown in the prompt. So this is a pretty interesting finding, because now we can think of several behavioral differences we can prompt with. Maybe we can have more agile sort of like driving motions, and then the model immediately tries to adapt to that kind of driving style. And similarly for different platforms, it could be how far you stay away from the walls, or how far you stay away from obstacles or humans and things like that. So we found this to be a fairly interesting construct. So as you can see, the right turn prompted model always tries to turn right as much as possible, whereas the other one just kind of tries to go straight. Okay, so what did we do with this? So this is interesting. Sure, it learns from safe actions and stuff like that, but is it just a navigation model? Not really. It's the most interesting thing that we found was that this representation, given that it's kind of encoding all of this mental models of the interactions, state action transitions, this is a general purpose representation that can be used for several things. So what we tried to do was we tried to take these pre-trained representations from PACT, and obviously the very first thing we tried was to actually deploy this in real life, because it was trained in simulation, and it didn't really have a lot of issues scaling to real life. So that was good. But at the same time, we also found that these embeddings that were constructed by PAC can be fine-tuned relatively quickly to localization, for example, and mapping. And as you can think about, these are also tasks that basically just depend on a history of states and actions, right? That's what happens to a series of states. Observations should give you some understanding of where you are in free space. Similarly, a history of the actions you've taken and the states and the observations you've seen can be combined into a local map. So basically, yeah, that's kind of the gist of what we try to achieve with this model, is to show that it is possible to build a more general purpose representation that can not only do the end-to-end policy, but also can be adapted for localization and mapping, and potentially even more things, such as more structured kind of navigation tasks. Okay, so yeah, so that's a quick recap about how the PACT architecture works. And if there's any questions, I can answer them, or if not, we can.
Hi, I had a quick question. I don't know if
Yes.
Hey,
yes, you're visible, yeah.
So I'm looking at this sort of from like an imitation learning perspective, but you're also regressing or predicting like the states alongside the actions, right? Were there any benefits to predicting the action or predicting the states that gave like performance boost to the policy itself? Or was it more towards like this is a more like versatile model that can not only do policy, but also some other things? Like, which was it?
It's somewhat of the latter. So that's a good question, because one of the ablations that we tried was initially we only started with just predicting the actions, right? So like how much signal can we kind of like backprop through the fact of predicting the action? And we found that a combination of predicting states and actions was more helpful in the versatility. So I would say it's a little bit of the latter. The other thing also that's interesting is we are not actually, reconstructing the observations or anything like that. So in the architecture up there, we were really only predicting the state tokens. right? So not the raw states. So it reduces the, the computational complexity you would need from the model, while still kind of maintaining this notion of regularization, and that's what contributes to the notion of world model. So I would think that this is what's benefiting the, the other downstream tasks as opposed to just the navigation.
Right. Kind of like, learning the world from
Yeah,
demonstration.
exactly.
Cool.
Exactly. Okay, so, all right. So now maybe I'd like to spend some time thinking about the limitations of fact, right? So sure, the notion being, if we have a data set of optimal trajectories, this imitation learning model, a learning from demonstration model, can try to mimic it as much as possible. But one thing that we can note is that there is no explicit notion of safety. Like, for example, fact never knows whether or not there is a boundary between safe and unsafe and what that boundary really is, right? So when faced with slightly out of distribution data, or maybe it's definitely robust to some small imperfections and things like that. But if you're faced with a different task or a different domain, a lot of the learning from demonstrations models might not scale very well, right? Because they've never seen unsafe demonstrations and they might not know where that boundary lies. So this might lead to imperfect policies when during deployment. So how do we typically handle safety constraints? The classical methods usually involve a complex mathematical formulation of the safety itself. And this would be translated into an optimization problem, and which would require some hand tuning of parameters and things like that. While this is all doable, one of the big limitations is the fact that, these typically operate in somewhat low dimensional spaces. And when we talk about issues where we have these, sensors like LiDARs or cameras that are viewing the world in a very abstract kind of a fashion, it's really hard to nail down exactly what part of it's contributing to the safety notion and how high dimensional that problem is. And that's why people have tried to approach this from a reinforcement learning angle as well, where you basically penalize all the unsafe transitions or failures and things like that. But at the same time, this also requires a lot of human effort in shaping the reward and trying to understand or isolate all of the failure cases and figuring out how to avoid them. And for that, we actually proposed an extension over PACT that we called CONBAT. As you might have seen, we have a thing for acronyms. So CONBAT is short for Controlled Barrier Transformer. And this is basically learning from demonstrations that's being extended to, the idea of how do we learn an explicit notion of safety. So the key idea is now the data set is not just an expert data set. It actually has carefully curated safe and unsafe demonstrations. And we are proposing we can basically collect synthetic data, because obviously we wouldn't want to do this in real life. And once we have a data set that's a combination of safe and unsafe, we not only learn the control policy, like we were trying to do with PACT, but we also learn what's called a safety critic. So this critic is essentially, the job of that is to evaluate the observations and try to predict, like, okay, how far am I from potentially crashing or being unsafe? And when we deploy this agent, this critic can help tune the policy further on the fly, and then keep it away from sort of like these unsafe zones. That's the key idea. So how does the CONBAT model work? A lot of it is similar to PACT, architecturally speaking. So similarly, we have the states and actions, and they're getting tokenized, and they are going through a causal transformer set of blocks, outcomes and embeddings. And as you can see, there is a block pi here, which is the policy head that we've seen before, that's trying to predict the appropriate action. There is phi, which is the world model, which is taking a state and action and trying to predict the next state token. But now we have an addition. We have the C, which is what we're calling a safety critic. So the safety critic is looking at a given state and an action at the current time step. And it's trying to predict two things. How safe am I currently? And how safe will I be if I take this particular action? So that's what's happening with the CT and CT+1. Those are essentially, think of them as safety scores. And the score, it could be a range that, that we like. It could be like between 0 and 1 or something like that. So if you wanted to achieve this, the biggest bottleneck is the fact that in the data set that we have collected, it would be hard to go and encode how relatively safe each state or each state action pair is. And that's going to be hard. The best you can do, especially in something like simulation maybe, is to just get a binary signal of whether have I crashed, or have I not? That's the easiest. Obviously, you can go in and handcraft a bunch of safety-related metrics to give you the data, but it's just not feasible, and it would be even much more harder if you want to do this in real life. So the way we kind of train this model includes several losses to account for that. So the very first thing, the most obvious one, is a classification loss that basically predicts, given this observation and perhaps the next potential state that I might be in, how, like, am I going to crash or am I not? So that's a classification loss, and it can directly use the binary signal that we have from the data set that's saying if it's a safe or an unsafe state. But at the same time, we also try to enforce what's called a smoothness loss. So we want the predictions of the critic to not just, be a step function sort of thing, but we enforce a certain delta on the slope of it. So, as we approach an unsafe state, we should get that signal even beforehand. That the agent will have to look a few steps ahead and then try to predict that, okay, there is a likelihood that I'm going to crash. So that's what the smoothness loss does. And there is also a consistency loss, whose job is basically like a regularizer, because as you can see, there are two critic modules here. One of them deals with the current time step, and one of them deals with the future time step. And just like how the world model would have to regress to the right kind of state token, this future critic will also have to regress to the value that's consistent with the next time step's critic value. Okay, so with this, the takeaway really is we are training an additional critic module, which is coming up with a more continuous sort of mapping from an observation to a safety score. And this is why because of the inspiration from control barrier functions, we're just calling this a control barrier transformer, because it's trying to learn the boundary and the transitions, as a robot maybe approaches that boundary. So now that's the pre-training phase. Sure, we have a critic, and how do we make use of it, right? And the answer is actually fairly simple. In the deployment phase, with Pact, we would predict an action and we would just take that action. And yeah, I mean, if it's a suboptimal action, there's not much you can do. You just have to rely on the model to give you the right kinds of actions. And often what happens with robots is that because of dynamic constraints of robots, even though the model at a certain point is aware that it might crash and it's trying to take, sort of like a reasonable evasive action, it might be too late because of speed, because of other, turning radius constraints and things like that. So that's the reason why the model needs to be able to predict this as soon as possible, as we're approaching an unsafe state and take an action. That's why the critic that we have trained now is obviously trying to predict a cost that looks into the future and tells you how unsafe you might be. And as we roll out this model for a policy on the fly, we execute a very lightweight optimization routine, like just a gradient descent, because we can take the cost and then we basically try to find what would be the optimal action that is minimally different from the proposed action that the model gives by default. And we basically try to solve this very small optimization problem to give us a slightly different action that would keep it safe. And because this entire fabric is fully differentiable, this is a fairly easy optimization problem to solve. And hence, we are now looking at a model that can sort of like evaluate the states on the fly as it runs. And if the critic says that, okay, in the future, there's a likelihood of like 50% that you might crash, it would have to adapt the action accordingly so that that possibility, the probability is lowered. So a very simple example that we started with was on this like simulated F1 track with a small agent kind of running around. If we were to train on a very simple track, which I'm showing here, the F110 playground, and if we test it on a more complex track, we see that Pact, which is on the left at the bottom here, it actually doesn't do that well, because it does okay on the train track, but because the testing track is so different and it's so much more complex, I think in this experiment, we ran about 128 episodes or something like that. And over all of these episodes, we are seeing the trajectory lengths are actually fairly short for Pact because it ends up crashing almost every now and then. And of course, we can fine tune Pact on this new data set from this new track. And even then, it's not doing that well. There's a few trajectories which might actually reach the maximum length of 1,000 time steps, but it's all over the place. I mean, some of them might crash very early on, some of them are reasonably okay. But Combat, on the other hand, we didn't even fine tune this for this track. So this was only trained on the very simple track. And the fact that the critic exists was helpful enough for it to understand what does unsafe mean. So basically, when it gets to the boundaries of the track on the left or the right, that's what crashing means, right? And it was able to translate that fairly easily to a new track, and you can see that there were basically no unsafe trajectories in the rollout. So yeah, just a very, very quick example of how the addition of this simple evaluator module can help with a learning from demonstrations pipeline.
So, Sai,
yes.
question on the difference between the packed frozen and packed fine-tuned.
Yeah.
So packed frozen is like you're using packed frozen that and like learning only the safety, like critical.
Oh, no, this was actually just packed without any of the the combat additions. So the packed will be trained on this track as it would try to predict some actions given observations. And if we put that same agent in the other Silverstone track, the more complicated one, yeah, what would the rollout look like? That's what packed frozen is trying to do. And packed fine-tuned was fine-tuned specifically on this data set. And even then, it's not completely optimal. That's what this figure is trying to say.
I see. So there, at no instant you had like just frozen on the packed and like just like fine-tuned to classify the safety critical modules.
Yes, that was actually a part of it too. So I think there was an ablation study that we did, which involved only like you learn the actions and the state predictions beforehand, and then you would fine tune for the critics. But the problem with that is, there is a benefit in using the safe and unsafe demonstrations for the packed part as well, right? Because the world model can definitely benefit from some of these boundary sort of like conditions that you would see in the combination of safe and unsafe. So that's one of the findings we've had. So it's definitely possible to fine tune the safety critic part as well, but it's, I don't know, it just has like a better scope, I think, if you train it on a data set that contains both safe and unsafe demonstrations. Okay.
And for this particular example, what is the observation space? Is it the...
Oh, the observation space is very simple. This is literally like a distance to either end of the track. There's a toy problem, basically.
I see. And
so it's like a two floating point numbers.
And the cost or the safety signal from the demonstration is either positive or
yes. It says a positive or negative, but the way, because of the smoothness loss factor, the critic learns is essentially like a more continuous mapping of like a between 0 and 1 kind of a value for the safety score. Okay, so and then we went back and tried combat with the similar like this office environment that we used for that you've seen in the video with PACT. So this is a more complex scene because now we have a LiDAR observation coming in. It's a scan with about like 720 values, like 0.5 degrees in the resolution and the angular. And we tried to compare this with several baselines, PACT itself, some imitation learning baselines such as behavior cloning, generative adversarial imitation learning, typical RL algorithms like PPO, TRPO, things like that. Again, the big takeaway is that reinforcement learning algorithms, like at least PPO and TRPO, don't do a good job. SAC was doing a lot better. So even though they have the luxury of learning from, I don't know, like millions of failure cases, it's still not capturing like the right sense of what this boundary of safety means. And interestingly, we also tried some approaches that were geared towards safe policy learning, such as constrained policy optimization, SACLAS. And here, the big issue that we found was the high dimensional nature of the observation itself. And it was hard to pose the problem for these models. And even with MPC, although it did do a fairly good job, yeah, the runtime of that algorithm was just massive, just because of how hard it was to pose this problem in like a classical sense and simplify some of these observation spaces. But PACT at the end of the day was doing somewhat okay. It's about 30% or maybe more in terms of collision rates, and Combat was the lowest of the lot at about a little less than 20%. But another interesting finding that we also had was the question would naturally arise, like how many negative demonstrations do you need to pull this off, right? Because unsafe demonstrations are hard to get, especially if we want to get some notion of it in real life, which by itself is very hard. And we found that even in the data set of negative samples that we've collected, even if we just use 1% of that, Combat is still above PACT, above a lot of the imitation learning. Well, imitation learning obviously does not use any negative demonstrations, so we already have an edge. And it's definitely above the classical like PPO kind of RL algorithms and somewhat on par with SAC. But even by using about 20% of the negative samples, we are exceeding the threshold of SAC. So again, it's interesting to think about what counts as a negative demonstration, right? So it does not mean that we'll have to start go crashing our vehicles. It can be as simple as just placing the robot in what could be construed as a negative sample, right? For example, I could go place the robot car in a place that's somewhat close to the wall, and I can encode that as, hey, this is an unsafe state. And the whole idea being it's just learning from the demonstrations, learning from that raw observation, which is probably an image or an LiDAR scan. It's essentially up to us to define, what do we call unsafe? And another interesting thing also is this can be, the fact that we have a smoothness loss and a more continuous mapping of the critic value means that it's up to us to place the threshold of what we believe to be safe. So for instance, if we are saying, the safety score between 0 and 1, a very aggressive driver could be thought of as somebody who is gets really close to maybe 0.1 or 0.05 kind of a threshold, whereas a very conservative driver is somebody probably staying very far away from the walls, and then that could be something like a 0.5, 0.6 kind of a safety score. And when we design this deployment phase, we can say like, okay, what is the minimum cost that I can afford to be at? And then we can use that value as something that would drive the optimization routine, and basically your policy would be adapted accordingly. Yeah, so that's a quick summary of the the idea of like how do we bring in safety. Obviously, there's a lot more to be done in this space because the next thing we are trying to do is basically look at more complex use cases with RGB images and potentially more safety constructs as opposed to just collision, right? Because now we might have to think about proximity to humans, or maybe when it comes to drones, for example, things like no-fly zones at different altitude levels and stuff like that. And how easy would it be to just learn those from a few demonstrations? Because the biggest issue with safety constraints is the expressivity of that. Like it's really hard to express them as specific rewards or like mathematical constraints. So how far can we go with just the raw data is the question. Any questions so far?
I have a quick question. Like, so for the pre-training fact, right? So, so generally when we say pre-training, you are looking at a data set which is more on the wilder side of things that are not kind of relevant to the task at hand. Like I'm talking about ones that you see in like computer vision and NLP settings, right? So here, for this particular project, seems like you guys have chosen the navigation domain, and the pre-training is being done on that. So question would be like how much of variety can it actually handle in terms of the targeted tasks, like downstream tasks?
Yeah, that's a great question. And the answer I think to that is it really depends on the objectives that we care about for the pre-training, right? So sure, right now in PACT, we have chosen to go with this action prediction and state token prediction and things like that, because we know that the signals of actions do exist in this data set. And oftentimes, when you think of something like Eco4D, for example, or Epic Kitchens and all of these different computer vision data sets, they don't have a notion of action per se. And there, I think I would view it as more of like a multimodal or like a video understanding kind of a problem, where we might have to bank on essentially, reconstruction losses, or maybe something a little bit more abstract perhaps, but more in the perception space of things, right? So it's sort of like self-supervised in the perception space. And we would try to just get a notion of what would happen in the future. So we're really only learning the world model. And one architecture that we have been playing with recently is actually called the multimodal masked autoencoder, multi-MAE. We found that to be pretty interesting because it could capture, essentially what would happen in the future concept from like an unstructured video or something like that. And we're trying to see like, can we adapt that representation and quickly fine tune to actions in a space that we care about? We would learn from unstructured data, but then now let's try to use those constructs and figure out, what happens with the robot. So yeah, I think more to be done on that angle, but yes, that's I think the real key for like pre-training for robotics, right?
Yeah, so I was able to see the difference because like you have state and action pair for the pre-training, which is more targeted towards robotics. So I wanted to get your the in like data distribution, like in distribution and out of distribution kind of thing.
Yeah.
But thanks.
Sounds great. So, okay, so now I'd like to switch gears a little bit and talk more about the language part of the work that we've been doing. Again, one of the biggest challenges is obviously with robotics when we have these task-specific modules, which are, curated in a very specific way, designed by experts, and they might not have very natural interfaces to modify them. Even if there are like minor changes in the hardware or the configuration of the robot or the placement of a sensor, changes in the objectives, it's actually fairly hard to go in and change those constraints. And one example that comes to mind is maybe going in and looking at raw XML files or something to figure out what I have to change to be able to do something slightly different. So the natural question is, how do we leverage, language as the most natural interface for indicating some of these? And can we, leverage some of the information that's already encoded in pre-trained language models or vision language models? So the very first problem that we tried to tackle, and the disclaimer is that this was actually before the time of, when ChatGPT and everything was really popular. So you might wonder about some of these choices, and that would be the answer. We tried to combine several constructs like language, vision, and geometry to see, can we have a language-based interface for changing trajectories or modifying trajectories based on some constraint that a user might express, right? For instance, okay, so this robot's trying to, bring a cup over there and it's going too close to the laptop. So the user can literally just say, I want you to, stay farther away, keep a much bigger distance from the computer, and it would adapt, in a natural fashion. So if you wanted to build up this flexible kind of an interface, and if we wanted to do this in a way that's agnostic to the form factor, so I would want to use the same interface with a drone maybe, or like a wheeled robot or something. How do I do that? And another example, right? So people might also have many different ways of expressing the same constraint. You could say, stay further away, stay far away, stay, all possible permutations of that sentence. And there might be a little qualifier, like, stay even further away, like a bit further away, things like that. And it has to adapt to those minor changes in the command as well. So how do we pull this off? So I'm gonna hit you with this heavy picture, but it's what's happening here is actually not that complicated. So two key things that we wanted to do. The first thing was we wanted to leverage information from pre-trained models. So we can bank on their understanding of language, their understanding of objects and images and things like that. So the very first block, which is the one in the blue dashed lines here, is a feature encoder. So it's learning from, it's using BERT to get features from, for example, a natural language command that a user might give, stay far away from the bottle. And then at the same time, there is also a bunch of images that we are perceiving of the objects, right? So we use CLIP to encode the images, and then we do some similarity on, the similarity between the command and the existing object features. So we realize, which objects are they talking about. And then the second block is a geometry encoder. So the idea here is that there is an initial trajectory that's being computed by, for example, like an existing planner. So this is, for example, like XYZ positions and the velocity, at each directional velocity at each time step. Now our job is to really try to modify this trajectory so it accounts for the command. And finally, we have a trajectory decoder. And this is, again, the continuation of your transformer model that is looking at the sequence, ingesting the features from BERT and CLIP to understand which objects are we talking about, and then slightly modify them, and then just send it back to whatever, constraint satisfaction like solvers that you have to give you the final, the control outputs. So that's mainly the idea here. So yeah, associating the objects in the scene with the language commands, and then kind of figuring out the field over which the trajectory has to be modified. So it, accounts for distance to these objects or proximity to these objects and things like that. So how do we pull this off? Obviously, it would be fairly hard to collect data sets from real life that involves a lot of different kinds of, text and images and robots and stuff like that. So we did something very simple. We actually just, for the object names and images, we literally just sampled ImageNet labels. And this would actually involve a lot of weird sounding objects as well. But we would sample some of these names from the ImageNet label space, and then we crawled Bing images to get representative images for each of these objects. And for the language inputs, we focused on 3 possibilities. One of them is translational changes, which are things like, say, go to the left of this, go to the right of this, or something like that. Speed changes, you could say things like, I want you to move slower when you're close to a human, so that the slower becomes a speed change constraint. And there are things that are like relative to objects as well. So things like, for example, in this video, we were saying, stay further away from the glasses, or like stay close to this thing or that thing. So those are somewhat more object relative things. Given all of this, we basically had this procedural generation loop that would sort of like come up with these statements. And for each of those statements, we would create a handmade tool that computes a force field based on the existence of the objects and the constraint that we've mentioned in there. So that would form the basis of like the ground truth trajectories that we train upon. So the fact that we're operating in the trajectory space is already somewhat, agnostic to form factors, right? Because every robot, regardless of how the control actions are achieved, really looks at a trajectory. So we were able to show this, work on arms, like we've seen in that video before. We've tried this in, the Copelia sim, and tried it out with a few different, robots like drones, and this, like, I think it's a hexapod, just going around a few objects. And the takeaway again here is this is not only able to handle, the XYZ positions when you say next to something and all of these things, but you can also say things like fly slower or go much faster or things like that. And this kind of indicates, the flexibility of the transformer model itself, right? Because now the sequence modeling, it doesn't really care what what we're expressing in the sequence, right? So we could potentially even think of more expressive, more expressive sort of things, like not only the proximity or the speed, but maybe there are like some torque limits or force constraints, and how do you grasp a certain object and things like that, right? So all of those can be expressed as well as an input to the sequence. But this was a very first foray of ours into how do we kind of integrate language, vision, and geometry. And I think the advantage that we found here is that we could leverage a lot of these existing features from Burton Clip, right? So this is not something we had to start training from scratch, and we didn't have to collect a data set of images like, in real life or things like that. And as these models get more and more powerful, like on the perception side of things, they would likely encompass a lot of objects of interest that we see every day. So unless, of course, there is a possibility that we might have very task-specific, unique objects, but a lot of the time, 80% of the way, I think we can definitely go by leveraging some of these models.
So just
yes,
a question.
yeah.
So what is the observation space for, let's say, the manipulation problem and this particular drone and the mobile robot?
Oh, it's all actually trajectories. So the input and the output are basically XYZ trajectories with, like directional instantaneous velocities. And we assume that there is a module that converts them into the right control commands. And the observation on the image space is obviously sort of like this, image of the scene with the objects.
So the assumption is that the entire trajectory is going to be visible in the...
Yes. Yeah, the entire trajectory is assumed to be pre-computed, and that's what we want to modify. It is possible to think of a more reactive planning kind of an approach, where you have a look-ahead window of a certain thing, and then you just try to modify that at every step. Of course, it depends on inference load, I guess, if you want to run like a replanning kind of a module. But of course, I mean, that might require an even smaller model because it's probably a shorter trajectory.
Yeah, I was curious to see, like, for the manipulation problem, where is the encoding of the 3D space happening to some extent? I'm like, there is a clip like text and image embeddings and stuff, but like I was wondering if the object poses. Okay.
Yes. So this is actually a typo. This should be n/3, not n/4. So the object poses are actually its positions, like XYZ positions. And then those are the 3D positions of the objects, and the entire trajectory is also sitting in the same space. So that's your like geometry part of it going into the model.
Thanks.
Okay. So yeah, any other questions?
No.
No. Okay. All right. So This is great. So yeah, okay, we can create models that can ingest text, and we can use multiple models. And but you can sort of see that there's a lot of architectural choices here also, right? Sure, we are leveraging existing models, but we still have to figure out how do we combine them? How do we translate those features? Like what kinds of metrics do we compute in order to ingest features from one block to the other, and things like that. And we still believe that we can reduce the barrier to entry even further. Like even if we wanted to come up with a scenario where somebody can talk to their robot as quickly and as easily as possible, we believe that, at this point, we still need a lot of expertise and development time to get there. And even then, even to sort of access these models and train them and maybe fine tune them, it takes a lot of effort. So then we started thinking about, that's kind of when ChatGPT came out and was taking the world by storm. And we started asking the question, okay, it looks like these language models are not just about language anymore. Like ChatGPT is already a combination of, codecs, because it can do code generation. It has all of the understanding of text. And at the same time, it has understanding of more this holistic common sense reasoning sorts of things. And it's, it's being shown that it reduces dev cycles in software and engineering on all of these different kinds of fields. So what can these LLMs do for robotics? That was the question that we wanted to ask. And basically what we tried to show was, by using something like ChatGPT for robotics, a typical pipeline, which would have an engineer sitting in the loop with an objective in mind, and they would basically write some code that deployed on the robot, and then they would have to monitor it, improve it based on the performance. We can replace it by something we're calling a pipeline that has a user on the loop. So the user would specify the objective, they would specify, some constraints and things like that. And most importantly, they would specify what tools or APIs the model has access to. So if you're working with for example, a manipulator, you could have, some control functions like, go to this position, move the end effector to that position, things like that, maybe grip an object, release an object. Those are all, existing APIs. And you just say, look, ChatGPT, these are all the functions you have access to. I want you to achieve a task. I want you to, arrange these colored blocks so you form the Microsoft logo. Or maybe I want you to fly a drone and inspect these shelves. And I want you to, have this embodied agent kind of walk around in this household space and figure out how to warm up my lunch. And yeah, so that's really the vision that we had for this particular work. And the hope is that the LLM is able to generate the code. And obviously we could stay in the loop and then kind of observe the code and give it some feedback, just like having a dialogue with ChatGPT. But eventually we could also envisage a version where LLM would interact maybe with the simulation and iteratively improve its own code. So that's kind of the whole idea. So how did we achieve this? So this pipeline basically has 4 steps. So the first step is, like I mentioned, we have to define a task-relevant robot API library. And one thing that we found to be useful is that this API library is not just like a list of all the functions the robot comes with. It's useful to wrap them in sort of more natural sounding functions, because it's a language model at the end of the day. So you can say move to position, or locate an object, or pick an object, and things like that. So when you name it that way, it becomes easier for the model to chain the behaviors together. And then we outline some principles on how we can build up a prompt. So, for example, here's an example on the bottom here. Imagine we're working with a household robot. The job of this robot is to do X, Y, Z. Some of the objects available around, I'm actually specifying the objects specifically here, but I'll show you there's a possibility we can use perception models to identify what the objects are. And then we list all of the main functions we can use. And then, can you make use of these to write code to go to the kitchen and make an omelet, things like that. Obviously, we are not actually using a robot to make an omelet at the stage, but it's just, spitting out some code, which sounds reasonable for that particular task. And a user on the loop in this version of our work would kind of look at the code, maybe deploy it in simulation, and give ChatGPT some feedback on what went wrong. And eventually we would get to a place where we can deploy this, right? So this example that we had of hey, can you use the blocks from the Microsoft logo? This was kind of an eye-opener moment for us, because we went to ChatGPT and asked it, do you know what the Microsoft logo looks like? And it said, yes. And it basically wrote an SVG of how that logo would look like if you were to draw it. And obviously when we used that, literally after that, we said, look, you have access to a manipulator arm. And these are the functions, go to position, grab an object, release an object. And I want you to arrange them in the Microsoft logo shape. And that's basically what's happening here. So it's able to relate. It's able to not only get something from its knowledge base, like on the remembrance of the logo, and it's able to, as you can see in this SVG here, it knows, for example, how far each of those blocks are to each other, where they're located and things like that. And it's able to put them in real life just based on this understanding. So that we thought was pretty impressive. So I know I'm running a little out of time, so I will maybe I'll probably skip this slide a little bit. But the most interesting findings for us from this ChatGPT work was that the first thing, it scales to multiple robots and tasks. So I'll skip some of the stuff in this video. But what we were trying to do is we tried to implement this with manipulators. So we would give it access to all the control API for a robot arm and ask it to do things like stacking, pick and place, arrangements. We put this in the AirSim drone simulator. So basically, what we tried to show in this particular example is if somebody were to do industrial inspection, which is a very a common field of application for drones, they would have these robots try to inspect these large structures like turbines or like industrial facilities and things like that. We found that to be as simple as just talking to the model. Like we would again give it access to some API, and it would essentially, we would just give it very simple things like, let's start inspecting the blades of the wind turbine. So this blade is about 30 meters above you, just fly up and down, and then something like that. There are like more comprehensive videos out there that we put out, which were basically like large missions that we would fly with drones, right? And then I ask it like, okay, you have to inspect the second blade, you have to fly this in a particular direction, fly that, take some images and come back, something like that. And I think the other one example we have is also with a real life drone. And again, very natural communication, right? That says, I just came back from the gym and I'm looking for a drink, and it just kind of like flies to the coconut water. And one thing to note here is that we actually encoded the positions of these objects in the scene, so it would know sort of like how to face them, where to fly, and things like that. And things like, okay, can you find something with sugar and a red logo? And I say, oh, that's probably a Coke can. And it relates to the fact that there is a Coke can in the scene and flies there. And again, let's skip to this different part maybe. But more interestingly, we found when we asked it to inspect a large shelf using a lawnmower pattern, it would understand the whole geometric constants of how to create the pattern, just writes the entire Python code, and has a while loop for like, okay, there are end shelves, so I have to fly this high, and then every step I have to go like back and forth, and it gives you explanations as well. So yeah, this is a quick summary of how it tried to do that inspection scenario using the lawnmower pattern. For the last thing, which I think is the most interesting thing with the ChatGPT work, is it was able to write perception action loops, right? So now we went a little bit further, just giving it like, control API, and we gave it access to tools, right? So we gave it access to, for example, a YOLO object detector. We gave it access to distance sensors that are sitting in simulation. And we said, I want you to achieve this task, and you have access to this object detection model. What would you do? So for example, this is an example where we use the AirSim simulator, and we say, to ChatGPT that you have access to an RGB camera, you have access to a depth camera, you have access to a YOLO-based object detector. I want you to explore this environment and find the objects that I'm looking for. And obviously, we would also specify some of the actions, like, you can move forward, you can turn left, you can turn right, things like that. So the output was a massive script, that basically it wrote that calls the YOLO functions accordingly, maps, the RGB pixels to depth pixels to get you get a sense of how far the objects are, how to move. So when I say find and navigate to a bottle, it kind of like explores the scene, finds that there is a bottle, sitting on the table, and yeah, that just goes there. I set a few more examples and like different kinds of objects and things like that. And we can obviously have more natural sounding questions as well. Like for example, that, find out where I can warm up my lunch. So it knows that a microwave is probably the most reasonable thing to do, and explores, it turns around, explores, and finds where the microwave is. And even beyond this, one thing we have explored a little bit and we are currently exploring is the notion of having a closed loop dialogue with GPT. So what we are trying to do here, it's just, this may be a little confusing, but we have a habitat scene with a few objects in there. And then habitat obviously gives the segmentation maps as ground truth, indicating what each object is. We are parsing that output and sending it to GPT at every step. So it's like, that's kind of like the brain that's looking at the scene and trying to decide what's the next action to take. So it says, okay, move forward by 1.5 meters and then turn left or turn right until you get to, we said, go to the chairs as the task, right? So this is a little annoying because back then we didn't have the API access yet. So we had to go put this in the dialog for the ChatGPT website. But obviously with an API in the loop, it would probably be a lot quicker. And yeah, probably skip this one a little bit, but what it's trying to do here is it again wrote some code that can do obstacle avoidance using a distance sensor. So there is a forward-facing distance sensor on this drone, and we just have to explain the fact that there is such a sensor. So it would write like this, reactive navigation sort of an algorithm that just avoids obstacles and flies to a goal spot based on what's in front. So yeah, I think anyway. So I know I'm a little bit out of time, but I'll wrap up quickly. What do we see in the future? I think that's really what drives us, right? The very first thing that pops into my mind, especially given the progress in the last couple of months, is the space of foundation models, and especially with GPT-4 and all of these extensions people are building on top of it. It's insane, right? For example, models like Segment Anything from Meta, Blip for captioning, and all of these interesting work on kind of like porting models into being more edge compute friendly, and also this idea, for example, this baby AGI and AutoGPT have been very popular recently, which are models, pipelines that let GPT kind of like refine its own outputs by working with tools or working with a simulation or something like that. So I believe this is a great area for research for robotics, right? Because we've seen some success on what GPT can do already. And imagine if we could link, for example, like a set of perception models with GPT, with a simulator of some kind, and just have it work on itself, until it achieves a task and it kind of understands what the right constraints are, the right way to solve it is. And yeah, so I believe that perception and reasoning using some of these off-the-shelf models would be a great starting point. And of course, then we'll have to figure out issues with safety and how do we translate that into control? What are the guardrails that we have to place on that kind of a model? And again, that's where all of these simulations or generative AI techniques will become key, because we would want to essentially predict, what's happening in the future, both in the physical like simulation space as well as robot sensory space, and that's where some of this generative AI technique can be helpful. And yeah, I think to recap, most of our work is open source. So the prompt craft robotics is where we are playing around with the prompts and stuff for the ChatGPT integration. We also have an integration with Microsoft AirSim, where you can actually, if you're interested, you can download it and you can chat with the drone essentially in the sim, and then you can just send it commands that go through ChatGPT, and then the drone would act accordingly. Same thing with Pact and Latte; those code bases are open source as well. Anyway, yeah, thanks so much for this, and this was fun, and I'm happy to take any questions.
I had a question. So how do you encode the post condition of an action? Like, how does it know it has reached a particular object in your second part of the work? Like when you integrate ChatGPT for, let's say, reaching the Coke can or the Coke can.
Yeah. So the Coke can example is somewhat simpler because we were basically giving it a set of waypoints that would indicate the position of an object, like the approximate position of an object. So the idea was the drone would just kind of like fly there. And we also had some orientations. So it would, try to get its own current orientation and then, face the object accordingly. So that was the easier part. When it comes to the embodied AI kind of examples where you said, go to the microwave, go to the bottle, it was leveraging the depth camera to figure out how close it got. So there were a few assumptions that we made. We assumed that there were no obvious like obstacles that it would not be able to see in between, for example, that would throw it off. But yeah, so in case it's an actual perception action loop, it was relying on like depth camera inputs and things like that.
Got it. And more of a general question, like, so we are talking about foundational models for robotics, right? Like, so do you imagine it to be like one single model for everything, or do you think it's going to be like a pack of models that somehow talks to each other to do these tasks? Because we have in your talk you've been talking about like different modes of or different form factors of the robots, right? So you have a better understanding of like what the future is going to be.
I believe it would be the latter. I don't think of it as one foundation model, because that would be too prohibitive to train it in a way that it adapts to a lot of different models. And it actually brings to mind one interesting paper I saw that I think literally just came out last week. It's called LLM Brain. So folks in that paper have tried to adapt, a combination of BLIP, actually this, language image pre-trained model, with ChatGPT and applied it to Habitat for exploration and navigation. So I see it in a similar way, right? So you can think of it as a stack of perception models or like a suite of perception models we can choose from. And maybe you can even have like a reasoning module like GPT kind of figure out which perception models to use. Like, do I need segmentation? Do I need tracking? Do I need something else? And that's like one portion of your model space. And then the next layer would be the reasoning layer, which is agnostic to robotics. It's not about robotics. It's not about form factors or anything. It's about common sense in a sense. So sure, it might be possible to fine tune against some of these models specific to our use cases. But my very high level vision is there is a perception layer, there's probably a reasoning layer, there's an execution layer, which is likely outputting code or maybe outputting actions and things like that. But of course, we'll have to still figure out like what's the deployment story of these models. Like, do we have those models running on the edge compute platforms, or do we have cloud connected robotics at some point in the future? We don't know for sure. But yeah, to answer your question, I think it would be a combination of at least different parts of the agent's brain in a way.
I think there is one question from the audience
Regarding the pact. How did the trained images, actions from simulation adapted well to the real world? The simulation environment was similar to the real world?
Actually, it was not super similar, but I think what helped it adapt fairly well was the fact that it was a LiDAR and not a camera. So even with a LiDAR, we had issues like, there was a lot of glass in these office spaces and you would have these reflections and, refractions and things like that. So there was definitely some sim to real gap. My hypothesis is that it's a combination of the fact that it is a LiDAR, so it's somewhat less susceptible to, domain changes, and the fact that over a large enough trajectory, the model is able to isolate what are the more salient parts of the sensory data that would actually, help navigate safely. But what still needs to be done with PACT is probably try it on a more extensive real life, kind of like deployments and see how far we can go with the simulation data set.
So, so I work on contact-rich manipulation tasks, like grasping and stuff. So what are we missing in order to integrate, let's say, the foundation models that we already have to that kind of manipulation settings? Any thoughts or?
That's a great question. I think one place where machine learning in general still has a problem is when it comes to precision. Right, so I'm sure, there are state-of-the-art techniques on the contact predictions and the grasping kind of space. But in general, when we look at these foundation models, these are all high-level perception heavy. They're like high-level reasoning heavy. So in the future, I think that's where I think I would like to highlight, the possibilities we have with simulations. I think really what we are driving towards as, robotics and AI in general is that we will try to leverage synthetic data as much as possible and keep training models that can basically figure out a lot of modalities. Right now, we're only focused on, RGB, depth, segmentation, things like that. But we do need, like grasp predictions or like, contact predictions and things like that. And I think there's been some interesting work done on like soft bodies and soft objects and things like that as well. But one way I can see foundation models being helpful is that we would have to train, I think, foundation models that can actually encode a lot of these different modalities that so far have not been of a lot of focus. But then the other thing is also, even if you look at industrial robotic scenarios or manufacturing scenarios or more precision contact-rich scenarios, there is always an aspect of reasoning about our tasks at hand. And oftentimes this would be given to sort of like these rule-based modules, or behavioral modules that are somewhat constrained. And that's where I see, again, some of these LLMs or something would play a role. And again, probably more fine-tuned versions of the current LLMs. We don't want, completely off-mark predictions, but yeah, so the perception part would have to be dealt with by somewhat more specifically trained models. And yeah, and then the reasoning part could come from existing, bodies of knowledge from LLMs and things like that. And some of these architectures, again, like the multimodal, MAEs or transformers or VIT architectures in general, they are powerful enough to scale to a large set of modalities too. And I think the whole 2D, 3D space of things, maybe associating images with object poses or like, contact and things like that, that might be a very interesting area of research.
Cool. Questions? Well, if there are no questions, I think we can thank Sai for his talk again.
Okay, thank you, everyone.